What's up everyone, welcome to the third part of Bootloader development mini-series, and in today's video we're gonna load kernel to memory and set up a cross-compiler so that you can program your kernel in C. Also, I recently created a Discord server, so make sure to join, link in the description. There is over 100 of you right now, so let's make it 1,000. Let's start this part by creating some more files. We're gonna have a build directory inside the root directory, of course, not in source. Move, okay. We wanna have a linker script script.ld. I'm gonna explain what linker is later. We wanna have a build.sh. It's gonna simplify the building process of our bootloader. And we wanna have kernel.asm inside source, and also kernel.c and kernel.h. These files, we're gonna fill them up with some code later, but just make sure you have all of them created, and this build directory. Okay, let's start setting up the cross compiler, and let me show you this article, GCC cross compiler on OSDEV. Of course, you have step by step for pretty much every operating system how to do it. I'm gonna do it for Linux obviously. And you can follow along with this article, or just follow along with the comments I'm pasting to the terminal. All of them you have in the description, and there is gonna be quite a lot of them. It can take you maybe even over an hour to completely install the cross compiler, so yes. Okay, so after running all of these sudo apt install commands, let's go to Firefox or whatever browser you're using and copy those links that I'm gonna show you in a second. So first you want to install GCC, and we're gonna go with the newest one, so 14.2, and GCC tar.gz, this one. Okay, and the second thing you need to download is binutils, like this, and also the newest one is gonna be here, tar.gz, this one. Once you have both of these downloaded, extract them to your home folder, or maybe even to the new directory. Let me create a directory first. So let's go to the terminal and make a mkdir source, like this, cd source. We're gonna go inside there, and let's go back to our downloaded files, extract here, sorry for this, extract to the source directory, so home, source, and select. So this is extracting, and GCC extract to the same directory, so home, source, select. Alright, once everything is done extracting, you can close this, you can type clear here. Actually, let's move to home directory. Now, copy these exports, paste them, enter, and now let's copy the commands that you have in the description. There will be a link to a text file or something like this, or maybe on my GitHub, we'll see. I mean, you already can see probably. So you're just copying this. These commands here. You just need to modify it slightly to the version of build.utils you have downloaded. Let me check which one was it. Where is it? Home, source, binutils 243. 243. All right. 243. Okay, so enter. Now make. Alright, and once this is done, after a couple minutes, make install. Great, so now we're gonna do basically the same thing, but with GCC. So let's go back to home and do these commands once again. So I'm just copy pasting. Also, make sure you have you have these exports ready. So if you close this terminal, you have to copy paste these 3 exports once again. This, and again we need to rename this GCC 14.2.0. 14.2.0. So let me change that and enter. Okay, what's going on? Yeah, this double dots, it is trying to go back and search for GCC 14.2.0 in the previous directory, so now it should work exactly. Right, moving on, this was the longest one so far. Next command, all target lib GCC. Great, make install GCC, like this. Alright, this was rather fast, and make install target lib GCC. So let me check if we have GCC installed, and yep, it works. Now let's go to build.sh. This is our bash script that is gonna make our life easier in terms of running the project, because remember, every time we do make call, right now we need to export all of these. So it's gonna be easier to just write a bash file for it and to just run build.sh instead of exporting all of this and make all them. It's just gonna be a couple commands less to paste. So that's it for build.sh pretty much. And in terms of kernel.c, I think we can do it now. It's gonna be a very simple. We just wanna load it. We don't wanna write a kernel. So include kernel.h void kernel main, and yeah, that's it. That's it for kernel.c. Let me just fill this kernel.h if endf kernel h define kernel h. Now we wanna export the main function, so just copy the definition like this, and endif. So that's gonna be our kernel. And now let's go to kernel.asm. And kernel.asm is gonna be this bridge between boot.asm and kernel.c. So in boot.asm we're gonna jump here, and kernel.asm is gonna call our kernel main function. So let's start with bits 32, because we are in 32-bit. Global start, and the start is gonna be a label that we're gonna create here. Start. Here you wanna call kernel main, and we need to export kernel main like this. Then we're gonna do an infinite jump like that, and at the end you wanna do times 512 $sign minus $sign db0, because you want to fill this segment to 512 bytes, and like the remaining bytes you want to fill with zeros. I think this is pretty understandable. We just want to keep this. We want to keep this 512 and this 512. So we need to fill the rest with zeros. All right, so this is going to be the kernel.asm. Now what we want to do is to load kernel from memory, and we're going to do it using BIOS interrupts, but remember they are not available for us in 32-bit protected mode, so we need to do it here before we jump to it. Let me define some labels. Kernel load seg is equal to 0x1000, and kernel start address, which is gonna be equal to 1 megabyte in hexadecimal, which is 1 and 5 zeros. 3, 5. Now let me make a comment here, somewhere there. We're gonna do load kernel. Let me first write the code, and then I'm gonna explain what each line means. Okay, let me actually make a change here. We want to move this under here. like that. Get rid of this useless space. And now one more thing at the end here, instead of infinite jump, we want to jump to code offset and kernel start address, so that this instruction will get us here, and here this will get us here, hopefully. We're gonna read from hard disk using CHS addressing. CHS stands for cylinder head sector, which are three values that combined together are an address of the place where we wanna read or write to. There are a couple articles that will tell you all the details about hard drive and CHS. I'm linking them all in the description, so definitely go check them out. Values describing cylinder head and sector are stored in CH, DH and CL registers respectively. If you look at the code, you can see that we want to read from head 0, starting from second sector, because the first one is bootloader, and cylinder 0. In the L we specify 0x80, which means that we want to read from the first hard drive. We set AH to 2 to indicate that we want to read. If you set it to 3, it's gonna do a write operation. AL contain the number of sectors we want to read, so basically the size of the kernel. This way of reading has some flaws, for example the limited size of data that can be read, so in a professional bootloader you would probably need to write a driver to do a better job. Before we go any further, I want to tell you more about the compilation process. Let's assume we are compiling a C code. We have 4 stages, starting with preprocessor, which handles instructions that start with hash symbol. So for example, include stdio.h is replaced with the content of stdio.h. The expanded code is then passed to compiler, where it's converted to assembly. Assembly code is then converted to object code by assembler. Next comes linker, which combines object code of library files with object code of our running program. In our case, it's gonna be boot.o, kernel.asm.o and kernel.o. Everything will be compiled into os.bin. This linker script defines how to link various sections of an object file into a final binary. Entry specifies the entry point of the program. Output format, pretty self-explanatory, specifies the format of the output file, in our case raw binary file, without any metadata. Sections are used to define memory layout. The choice of sections differs for every output file. In our case we'll have .text, .arrowdata, .bss and .data. All of this info I got from this documentation. It's very detailed and explains everything you want to know about linker file. You don't need to read all of it, of course, but if you have any questions about linker script, you have the link in the description. Okay, so pretty much the last thing is to set up the Makefile. nasm-f elf-g source kernel.asm-o build kernel.asm.o. So this build directory that we created here, we'll hold the object files. Then we go i686-elf-gcc -capital I source $flags. This is sort of like a placeholder. We can here declare flags later instead of writing them here, because we're gonna use it multiple times, and actually we'll have another one files here, but this is we're gonna fill it later. So flags -std gnu99 -c source kernel.c -o build kernel.o. Oops, here / instead of dot. Alright, and we can I misspelled elf. Okay, so we can copy paste this ld -g relocatable $files here -o build complete kernel.o, and what this basically does, it's gonna combine kernel.o and kernel.asm.o into complete kernel.o. Alright, so next we can copy this, because we wanna do it like that, flags -t, and we specify linker script, so source linker script.ld -o bin kernel.bin -ff freestanding, like that, capital O 0, so no optimization, no stdlib, build complete kernel.o. Let me copy this. Okay, great. And now, what we want to do is to use dd, which is gonna write everything to this to os.bin basically. And so yeah, let me do that now. If bin boot .bin double like arrow key bin os.bin. Now you can copy this, and here you wanna do kernel.bin, and here you wanna fill the, because we want to have like a couple sectors, right? So let me show you dev 0 bs, which is one sector size, and it's gonna be 512, and count. We wanted to load inside the boot.asm, if I remember correctly. We specified 8 sectors to read, so let's make it 8, because why not? Of course, the kernel, like the actual kernel, would be way bigger, right? So you have to keep that in mind. But this is just to show you how this works, like a proof of concept sort of thing. os.bin. So what this is gonna do? It's gonna append first boot.bin inside os.bin. Just after os.bin, there's gonna be kernel.bin. And remember, thanks to this instruction, boot.bin is exactly 512 bytes, sorry. So one sector. Kernel.bin is the exact same size thanks to this. It's gonna be exact same size thanks to this. And here we're gonna just fill the remaining part with zeros. No, sorry, actually it's not gonna be, wait, I'm talking, I wasn't right. It's not gonna be exactly 512, because kernel.bin is from complete kernel, and complete kernel is comes from kernel.asm, which is 512 bytes, oops, combined with kernel.c. But this thing, wait, I lost it. This is gonna do the job. So just make sure to in make clean remove all of them. So we want to remove bin kernel.bin, we want to remove -f bin os.bin. What else? We want to remove all the object files all the object code. So it's gonna be build kernel.asm.o, remove -f kernel, build kernel.o, and remove -f build complete kernel.o. And this should be enough. So yeah, this is how the, oh wait, not it's not how the Makefile looks, because in files we need to specify this one and this one. And in flags, what you want to do is -g to enable debugging symbols, -f free standing, -no stdlib, -no start files, -no default libs, -wall, capital O0, and -i inc. Okay, so let's test what we just did. Open up terminal, go to the directory you have your project in my case it's documents bootloader, like that. Make sure I've already done that to do chmod +x build.sh to make this executable. Alright, so make clean build.sh. As you can see, we have 4096 bytes in total. Let me go to the bin directory ls and let's do bless os.bin. And in this hex editor you can see all of our all of the codes combined, linked together, and the segments filled with zeros at the end. Alright, so let me clear and let's open up JDB, which is a GNU debugger, very popular, and I think it's pre-installed, so you should have it. So let's start by adding a symbol file, because basically I want to show you that we can run kernel main. So we're gonna set up a breakpoint there and make our debugger go there, so you can actually see that it is there. So complete kernel.o and the address 1 2 3 4 5. Press Y. Now break kernel main like this, and now target remote qemu -system -x86 64 -hda bin os.bin -jdb stdio -s. Wait, stdio-s. And this should run the debugger. Now, if you type C to continue, you can see that we are in kernel main. So at kernel main at source kernel.c. So you can see that it indeed goes and executes the kernel main function. And that's the end of the series. Thanks for watching. Let me know what can I do better next time. Like, subscribe, and as always, see you soon.